Welcome back to the deep dive. If you've been tracking the AI landscape, you know that the sheer uh, complexity and cost of training these modern foundational models is just staggering. It's not about having a big server anymore. It's an infrastructure challenge on on a continental scale.
It really is. It's an arms race.
Yeah.
And it's fueled by this hyper-specialized hardware.
Uh-huh.
Now, when we talk about a training run for something like GPT-4, you're looking at costs in the range of $100 million.
Yeah.
And that's already climbing.
100 million.
And some of the big centralized labs, like Anthropic,
Mm-hmm.
they're now pursuing efforts that could push past $1 billion for a single project. And this isn't just generic compute. It demands these massive, massive clusters of NVIDIA H100s or B200s, all knitted together with these ultra-fast proprietary interconnects. Things like NVLink and InfiniBand.
And they all live inside a handful of tightly controlled data centers.
Exactly. That infrastructure alone creates this enormous barrier to entry. It's a massive moat that only a few of the tech giants can even afford to think about crossing.
Right. But here's the paradox, and this is really the problem we're going to tackle today. AI needs these massive, diverse, global data sets to actually generalize well, to be truly smart. But the best data, the really valuable stuff from finance or patient health records, private user activity, it's all locked up.
It's locked up, and for good reason. It's sitting in these organizational and regulatory silos. You've got GDPR in Europe, you've got HIPAA for medical data, CCPA in California. The list goes on.
And no sane corporation is going to risk a massive data breach by just dumping all that raw, sensitive info onto a central server, even if it would make the AI model way better.
Precisely. So you got this fundamental tension, right? AI needs data diversity to get smarter, but privacy laws demand that data stays local. So how do you solve that?
That is the mission for this deep dive. We're looking at two major kind of intertwined movements that are trying to address this exact privacy paradox. First, the more established one, the one that came out of academia, really.
Right. Federated Learning, or FL. Its core idea is actually pretty simple. You move the computation to where the data already lives.
And then there's the second movement, which is where all the innovation is just exploding right now, decentralized AI training networks.
Yeah, and these are leveraging the permissionless and incentivized infrastructure of crypto and Web3 to create these truly global trustless systems. They're capable of coordinating these massive training runs across hardware that's distributed all over the world.
So we really need to understand both to see the full picture.
We do. We'll start by laying the foundation with federated learning. We'll explore its 4 biggest scaling roadblocks, and then we're going to dive deep into the specific architectures, the crypto-economic models of these bleeding-edge projects. We're talking about Nilus, Prime Intellect, Pluralis, Templar, and Gensen.
And then at the end, we'll weigh all the technical trade-offs to figure out which of these systems actually offers the most verifiable privacy guarantees.
Okay, so let's ground ourselves in the basics of FL first, because it really does require a complete flip in your thinking compared to traditional machine learning. If traditional ML is all about forcing the data to come to the server, what's the fundamental shift with federated learning?
It all comes down to location. In the conventional approach, you gather every single raw data point, all the patient records, all the text messages, all the financial transactions, and you put them on a centralized server for processing.
Right.
FADIL is the complete opposite of that. It insists that the data has to remain local on the edge device or the client. The core shift is moving the model, the computation, to the data instead of moving the data to the computation.
That sounds great in theory, but how does the actual learning happen if all the data is spread out? I think walking through the learning cycle step by step is probably key to understanding the privacy benefit here. It is. It's an iterative, collaborative process. So, step 1. It begins with the central server, the orchestrator, and it initializes a generic baseline model.
Okay, a blank slate, basically. And then step 2.
In step 2, that central server securely distributes copies of that generic model to a selected set of client devices. And these clients are super diverse. They could be individual mobile phones, they could be powerful servers in a hospital consortium, or even industrial IoT devices.
And then the really critical part, step 3, the local training.
This is it. The clients train that model locally, using their own proprietary private data set. The crucial part here is that the raw data never leaves that device. This local training optimizes the model based on that client's specific information, so it effectively personalizes it just a little bit.
And step 4 is where the privacy genius really comes in. They're not sending raw data back to the server, so what are they sending?
They only share encrypted model updates. These are the parameters or the gradients. Basically, it's a numerical representation of how the model should be adjusted based on what that client learned locally.
So it's instructions, not information.
Exactly. And this update is often secured using techniques like secure aggregation protocols. That ensures privacy even from the central server itself.
Okay, so the server gets, I don't know, dozens, hundreds, maybe millions of these encrypted numerical instructions. Step 5 is the aggregation.
Right. The central server takes all these inputs, combines them, and often just averages them together. And that creates a new, generalized, and improved global model. This averaging process is how the model benefits from the entire network's diversity without ever seeing the raw data from any single client.
And finally, step 6, you close the loop.
The new improved global model is then sent back down to the clients for the next round of training, and the cycle just repeats over and over. The global model gets more and more robust and accurate with every iteration, and it's leveraging these massive diverse data sets while fundamentally respecting data locality and privacy.
That distinction, updates versus raw data, that's the technical core of this whole thing. Now, the sources categorize FL based on who or what is actually participating. You mentioned two main settings.
I did, yeah. The first is cross-device FL. This is the scale-out problem. You're dealing with a massive number of devices. We're talking millions, like consumer mobile phones, smartwatches, little IoT sensors.
And they're not reliable.
Not at all. They have volatile connectivity, limited battery life, limited resources. You need massive participation, but devices are dropping out constantly. This is the classic setup for personalized features like, say, next word prediction on your phone's keyboard or optimizing your fitness tracker.
So millions of Flickr devices, but a huge amount of data overall. What about the other category, the more institutional one?
That's cross-silo FL. In this case, the number of participants is small, maybe 5, 10, 50 at most. These silos are large organizations, data centers, institutions like banks, hospitals, or manufacturing plants.
Right.
They have stable, powerful connectivity, and they hold huge volumes of extremely sensitive data.
So the goal here is more like consortium training.
Exactly. Data volume is high, but the participant count is low and trusted.
And we also have to differentiate based on the network structure itself. Traditional FL relies on that central server, so centralized FL, but that introduces its own risks, doesn't it?
Absolutely. The central server coordinates everything. It selects the clients, gathers the updates, does the aggregation. If that server fails, the entire process just stops. It's a single point of failure, and it's a single point of data risk, even if it's only handling encrypted updates.
Which naturally leads to the idea of decentralized FL, which gets rid of the server entirely.
Correct. In that model, updates are shared only among the interconnected edge devices directly, peer-to-peer. There's no central orchestrator.
So you eliminate that single point of failure.
You do, but you pay a price. The resulting model's accuracy becomes entirely dependent on the network topology and the consistency of the communication among those edge devices. It just introduces a lot more complexity to get the model to converge properly.
And finally, there's the category that has to deal with the messy reality of the real world. Heterogeneous FL or hetero-FL.
This is non-negotiable for any large-scale application. Hetero-FL just acknowledges that real-world clients vary wildly. In hardware, an old phone versus a new server, in software versions, in computational power, and critically, in the type and quality of their data. Classical FL just assumed everything was uniform.
Which is never true.
Never. So hetero-FL specifically develops algorithms to generate a single high-quality global model, even when it's being trained over all these highly varied local models. It's what makes this polemical across the diverse systems we all actually use. You know, the narrative of FL really shifts AI from being the centralized resource hog to a more collaborative distributed tool. And this transition is driven by really three huge benefits that solve that privacy paradox we started with.
Okay, let's start with the one everyone cares about most, privacy and security. You mentioned the benefit is twofold.
It is. So first, you have the fundamental privacy guarantee. The training happens locally on the edge device. The raw data never moves, which eliminates that huge risk that comes with centralizing sensitive information.
Right.
And second is security, which focuses on the model updates themselves. Only the encrypted parameters are ever shared.
Tell us a bit more about those secure aggregation techniques. How does this system make sure the central server can't just decrypt one individual's contribution and spy on them?
The sources really emphasize what's called the secure aggregation principle. So imagine a massive lockbox, but with multiple keys. Individual clients encrypt their updates using keys that are shared among the whole aggregation group.
Okay.
The central server can only unlock the box and see the aggregated result if a sufficient number of participants have submitted their updates. It decrypts only the combined average, not the individual inputs. So if a client drops out, the system literally cannot decrypt that partial input.
So the contribution of any single client remains confidential, even from the
It's
orchestrator.
exactly. That level of protection is just essential.
And beyond just secrecy, FL dramatically improves the actual AI model itself through diversity.
This is the diversity and generalizability benefit, and it's huge. By accessing data that's spread across global locations and organizations, different languages, different demographic samples, different clinical patient histories, you inherently get much greater data diversity.
And models trained on that diverse data are just more robust.
Significantly more robust. They generalize better to real-world, messy scenarios, unlike models that are trained very narrowly on some pristine, centralized data set.
And for any organization that deals with sensitive information, the third benefit is the immediate relief it offers for their compliance teams.
Oh yeah, regulatory compliance is a massive economic driver for this. Because the whole design mandates data localization, FL inherently helps satisfy the requirements of privacy regulations like GDPR, CCPA, and HIPAA. It minimizes data movement, it minimizes pseudonymization requirements, it just simplifies the whole legal and logistical burden of managing highly sensitive personal or health information.
Let's talk about real-world impact. Where is this making the biggest difference right now? Healthcare seems like the perfect fit for that cross-silo FL model.
It's the canonical use case. I mean, think about something like heart attack risk prediction. Hospitals can jointly train these really sophisticated diagnostic models leveraging collective patient data from across the globe without ever having to physically share a single patient file. This could dramatically accelerate medical research.
And we've seen specific frameworks mentioned in the sources that are being used to achieve this across distributed, sensitive data sets.
Absolutely. We're talking about frameworks like Splink, which is used for secure distributed genome-wide association studies, or GWAS, and things like GLORE and EXPLORE for electronic health records classification and image classification.
So this is already happening.
It is. These frameworks prove that large-scale, complex medical analysis can be done collaboratively across multiple institutions, and it overcomes all those traditional barriers of data sharing.
Meanwhile, cross-device FL is kind of silently optimizing the devices we're all using every single day.
Yeah, the most common example is on our mobile devices. The next word prediction in your keyboard, voice recognition, face detection. These features aren't sending all your private text or photos to a central server. The model adapts to your personal speech and writing patterns. It trains on your device, and it only sends back that generalized update.
So it enhances the app's functionality through personalization while strictly preserving the privacy of the underlying data.
Precisely. And finally, you're seeing it move into the industrial space manufacturing and AR/VR.
How does that work?
Well, in manufacturing, FL can help optimize supply chains or improve product recommendation systems by leveraging diverse data from multiple partners, but without anyone having to share their trade secrets. For industrial environmental monitoring, it lets you do time series analysis using sensor data from multiple facilities, which can improve efficiency and preempt failures.
And in AR/VR.
There, the technology can refine object detection and spatial mapping, which are used for remote operations or training simulations by learning across multiple user environments at the same time.
Okay, so federated learning sounds like the perfect solution. But you mentioned earlier that scaling it up outside of these highly controlled institutional environments introduces these fundamental problems that traditional distributed training in a data center just doesn't have to face. What are these four roadblocks?
Right. They all basically stem from the environment. Centralized labs get to operate in this homogeneous, high-speed controlled world. FL has to operate across the diverse, unreliable, global internet.
Roadblock number one, expensive communication. Why is this such a huge problem for FFL compared to other kinds of distributed computing?
It's purely a matter of speed and volume. I mean, federated networks can involve millions of devices, all communicating over standard, slow, congested networks. The communication overhead on the internet is just orders of magnitude slower than local computation. But the model still needs to exchange millions of parameters frequently.
So even though you aren't sending the full data set, you're still sending this huge representation of the model after every training iteration.
A huge one. And the sources identify FL as generally the least efficient approach from a communication standpoint compared to the other privacy-preserving alternatives we'll get to later.
So if communication is the bottleneck, the solutions must have to focus on reducing the size and the frequency of those messages.
Exactly. Researchers are prioritizing these communication-efficient methods. This includes things like instructing clients to increase their local training iterations before they send an update, so train more locally, send less often.
Okay.
It also involved aggressive model compression schemes, things like quantization, which is reducing the precision of the parameters, or implementing sparse updates, where you only send the parameters that have changed significantly. That dramatically shrinks the size of the files you have to transfer.
And then roadblock number 2 deals with just the sheer variation of the clients. Systems heterogeneity.
Yeah, this is the chaos factor. You're mixing iPhones with old Androids, industrial sensors with high-end PCs. They differ wildly in hardware, software, processing power, and network reliability.
So out of a network of millions, only a small, maybe biased fraction might be active at any given moment.
Right. And this creates stragglers, these slow devices that drop out and stall the whole synchronous training process. And it often leads to the selected training set not even being representative of the whole population.
So how do researchers introduce resilience into a system that's basically designed for chaos?
You need fault tolerance. So solutions include using asynchronous communication, where the system doesn't just sit and wait for the slowest device, and also intelligent active device sampling to deliberately avoid constantly picking known slow participants.
You mentioned a specific framework, FedProx.
Right, FedProx is one of the most important optimization frameworks developed for this.
Okay, you said it adds a proximal term to the local loss functions. That sounds like some pretty impenetrable math jargon. So in plain English, what does that proximal term actually do for the system? Is it like a rubber band pulling the local model back toward the global center?
That is a perfect analogy. Yes, you could think of it exactly like a regulatory mechanism, a rubber band. When a client trains locally on its own data, its model wants to diverge, right? It wants to get really specialized based on its own unique biased data. The proximal term is a mathematical penalty that gets added to the local training. And this penalty increases the further the local model tries to drift away from the current global model.
So it constrains the optimization.
Precisely. It prevents the local models from becoming too specialized or divergent, which is critical for maintaining robustness against that system heterogeneity. Preventing stragglers from completely ruining the global model, and crucially, against the next roadblock, statistical heterogeneity.
Roadblock 3. Statistical heterogeneity or non-IID data. This is the data quality problem, where the data sets are not independently and identically distributed.
And this is a fundamental flaw in pretty much any real-world data application. I mean, if one hospital only sees pediatric cases and another only sees geriatric cases, their data is non-IID. If a user only texts in Spanish and another only in French, their mobile data is non-IID.
And when you average the updates from these disparate biased data sets, the global model struggles to converge.
Right, it leads to model drift or even divergence. It just can't find a good average.
So how do we fix this fundamental data imbalance?
You have to address it algorithmically. So solutions include developing personalized models for clients that account for their local data characteristics, or using weighted aggregation, which gives higher importance to clients with data that's deemed more diverse or representative of the overall target.
And there's a more sophisticated approach too, right?
Yeah, Federated Learning, or QFFL.
And what does QFFL prioritize?
It prioritizes fairness, not just speed. QFFL is designed to encourage a fairer accuracy distribution across all the clients. It adaptively imposes a higher weight on updates coming from devices that currently have a higher loss, so the devices that are struggling the most. It pushes them toward the global minimum and ensures no single client gets left behind or biases the model too heavily.
Okay, and finally, roadblock 4, which brings us full circle back to privacy. Security and privacy vulnerabilities. If the parameters are all encrypted, how are adversaries still able to compromise the system?
Because encryption alone isn't sufficient. There are two primary risks. First, inference attacks. An adversary can analyze the encrypted model updates, looking for patterns or artifacts that allow them to infer properties of the underlying private data. They aren't seeing the data itself, but they can infer characteristics about it.
Wow.
And second, and this is often more insidious, are data poisoning attacks. This is where hostile clients deliberately manipulate their local training data or the updates themselves to mislead or corrupt the global model. They can insert backdoors or cause specific errors.
So FL is great for compliance and for scalability, but it is not a complete privacy guarantee on its own. It needs to be augmented, which brings in those 3 traditional privacy techniques.
Correct. These 3 stopgaps are essential for sensitive applications. You have differential privacy, DP, which involves adding carefully calibrated noise to the updates. This ensures statistical indistinguishability. It makes it mathematically difficult to tell if any single individual's data was included in the training set or not.
And then the cryptographic approaches, homomorphic encryption and secure multi-party computation.
Right. Homomorphic encryption, HE, is kind of the powerhouse of encrypted computation. It allows the central server to perform computations like adding or averaging updates directly on the encrypted data, on the ciphertext, without ever needing to decrypt it
So the information stays private through the whole process.
the whole time. And then secure multi-party computation, SMPC, is a more collaborative approach. It allows multiple parties to collaboratively compute a result over their inputs while keeping those inputs private. In FL, it's primarily used for secure model aggregation, ensuring that the computation for averaging the updates is distributed among different owners who jointly compute the final result without revealing their individual input shares.
Okay, so we've established that institutional FL is great for these highly regulated, trusted, cross-silo collaborations, but it still fundamentally requires a central, trusted orchestrator. Now we need to pivot to the decentralized revolution, which tries to get rid of that trusted middleman entirely.
And this pivot is really philosophically driven. It's about addressing the immense power that these centralized labs have over foundational models, which often limits access, transparency, and really stifles open source innovation. Decentralization wants to leverage the world's untapped, unused GPU power in a totally permissionless way.
Let's clarify a distinction first. Distributed versus decentralized training. They sound similar, but they operate on fundamentally different trust models.
They are worlds apart when it comes to governance. Distributed training just means a model is split across different machines or geographies, but it's done by single or multiple permissioned entities. They're known, they're whitelisted, they're trusted.
But decentralized training is different.
Completely different. It relies on a permissionless, incentivized network where separate nodes contribute work using crypto infrastructure, smart contracts, tokens, on-chain coordination to establish trust where none is assumed to exist.
So if these decentralized networks want to truly challenge the centralized labs, they have to overcome those same force-scaling roadblocks we just talked about. But now they're magnified by the permissionless nature of the system.
Absolutely. The first roadblock, communication overhead, it becomes extreme.
Right.
We mentioned centralized labs use these proprietary high-speed fabrics like NVLink, moving data at 1.8 terabytes per second within the cluster.
That's insane.
It is. Decentralized networks have to coordinate model updates over standard consumer-grade internet speeds. If they can't dramatically compress the data and manage latency, the training will just be catastrophically slow.
And the second roadblock verification is now existential. If you don't trust anyone, you need ironclad proof that the compute being done is actually correct.
Yes. Due to the permissionless nature, verification has to be robust enough to prevent Sybil attacks, where one entity pretends to be many. It has to prevent malicious inputs or stop contributors from just submitting garbage work to claim rewards. They need trustless mechanisms to ensure the compute is productive and valuable.
Third, they still face the compute heterogeneity challenge, but on a global scale and without the ability to, physically inspect the hardware.
Right. They are coordinating highly varied, often older, consumer-grade hardware across every single time zone. You need incredibly sophisticated scheduling and fault tolerance to use this global heterogeneous compute pool efficiently.
And finally, the ultimate crypto-economic challenge: incentives, funding, and ownership.
This is the revolutionary part. In centralized labs, the company takes all the upside. Decentralized networks have to create these crypto-economic models that effectively reward the GPU providers, the validators, and the model designers themselves.
So they need incentive structures.
Right. Things like staking, slashing, token rewards, things that guarantee integrity and sustained contribution, all while distributing the ownership of the resulting model, unlike a traditional corporate monopoly.
It's clear these challenges are immense. But you mentioned a convergence trend where teams are succeeding, which suggests they are finding ways around these bottlenecks by combining optimizers, compute exchanges, and on-chain coordination. They're creating these modular, open pipelines that are starting to look competitive.
They are, and that's why we need to look at the specific technical details of how they're overcoming these communication and verification bottlenecks. Because this isn't theoretical anymore. These networks are executing multi-billion parameter runs today.
Okay, let's get into the specifics. Let's start with Noose Research. They came to prominence through their work in open source AI even before they dove into decentralized training.
Their early contributions were really significant. They successfully solved the context window extension problem with something called YARN. It scaled large language models up to 128,000 tokens, which is roughly the length of a classic novel like The Adventures of Huckleberry Finn, and they did it without expensive full retraining.
So that established their credentials in optimizing large models.
It did. But for their decentralized efforts, the focus really shifted to overcoming communication lag, and that's where decoupled momentum optimization, or DIMO, comes in.
And what does DIMO do?
DIMO is their communication breakthrough. It reduces overhead by an astonishing factor of 10x to 1000x.
Wow.
So traditional training requires every single parameter to be synchronized constantly. DIMO figures out that only the parameters that are changing the most rapidly actually need that tight synchronization. By filtering out all the noisy, slow-moving updates, they drastically cut the amount of data that needs to be transferred.
And they use compression, too.
Yeah, aggressive compression methods, similar to the discrete cosine transform, DCT, that JPEGs use to compress images, they apply that same idea to their parameter updates.
And this optimizer is built into their coordination framework, Psyche. What does that architecture look like on the Solana network?
Psyche is a really sophisticated coordination layer. Solana acts as the highly performant accountability layer for recording all the commitments. And the network involves three key roles. You have clients, who are the GPU providers, a coordinator who tracks the model state, and witnesses.
Okay, what are the witnesses, and how do they ensure trust in this trustless system?
Witnesses are randomly selected clients, and they're responsible for verifying the work done by the primary clients. But they don't rerun the full training. Instead, they submit these lightweight cryptographic summaries of the work, often using structures like Bloom filters, to the coordinator.
Okay, Bloom filters, that's more jargon. Can you break down what a Bloom filter is and why it's so useful here?
Sure. A Bloom filter is essentially a probabilistic data structure. Think of it like a very compact fingerprint of a set of items. It can tell you with 100% certainty if an item is not in the set, but only with high probability if an item is in the set.
So it's a space-efficient way to check for membership.
Extremely. So in Psyche, witnesses use them to quickly verify that a client's contribution aligns with the required training run parameters, but without needing to submit these massive proof files. It's all about efficiency.
And, critically, Psyche enables asynchronous training.
Yes. This is how they try to approach data center speeds. Instead of waiting for the slowest GPU, the straggler, GPUs submit their batch updates and then immediately start on the next batch. This asynchronous approach minimizes idle time and maximizes GPU utilization, which is essential to achieve competitive training throughput.
And they're putting this to the test right now with the Consilience run.
They are. A 40 billion parameter transformer pre-training run, that's a significant commitment in the decentralized space. And they've learned some painful lessons along the way, like dealing with loss spikes, which they address by rolling back and using safeguards. One is called Olmo's skip step mechanism, which automatically skips any gradient update that deviates too wildly from the network average.
Because that prevents a single malicious or faulty node from corrupting the entire run.
Exactly. Now, moving on to Prime Intellect. Their focus also heavily involved aggressive communication reduction, notably with something they called Open to Loco.
And what were the results there?
Open to Loco demonstrated spectacular efficiency metrics. It achieved 90% to 95% GPU utilization, proving that even over consumer networks, distributed training could be highly efficient. And crucially, they achieved this while relying on 500x less communication compared to centralized synchronous training models. That validation showed that their fundamental architectural difference was sound.
And their Prime framework addressed the inherent flakiness of global hardware.
It did. The Prime framework is built around elastic device mesh. This is a dynamic architecture that allows compute contributors to just drop in or out of ongoing training runs on the fly without halting or crashing the whole process.
That robust fault tolerance seems mandatory for any permissionless system.
It is, and they demonstrated this by training Intellect 1, which was a 10 billion parameter model, across 3 continents in about 6 weeks. They sustained 83% utilization overall, which proved the elastic system actually worked in practice.
They also integrated incentives using Base, right?
Yeah, their protocol layer is currently coordinated on Base, which is an Ethereum L2 testnet. For their Intellect 2 RL run, they tested a cryptoeconomic model where contributors had to stake testnet tokens that could be slashed if their work was found to be invalid.
So staking provides a collateral layer that enforces honesty.
Exactly. They also introduced Shardcast, which is a system to efficiently distribute the massive model weights peer-to-peer across the network, sidestepping the need for a single centralized download source.
Okay, now we come to pluralis research, and they have a huge architectural distinction. They use model parallelism instead of data parallelism.
Hmm.
Why is this distinction so critical for the future of decentralized AI?
This is a key architectural divergence, and it's worth pausing on. Most decentralized networks use data parallelism. So everyone holds a copy of the model and the data is split up. Pluralis uses model parallelism, which means they split the individual layers of one single huge model across multiple different GPUs.
So model parallelism solves the problem of fitting a frontier Model 1 that's too large for a single consumer GPU onto low-end hardware. But doesn't that introduce a massive communication bottleneck? I mean, every time an activation moves from one layer to the next, you're communicating across the unreliable global internet. That has to create pipeline bubbles, right? Wouldn't that destroy your utilization rate?
That is the classic central problem with pipeline parallelism. You get these bubbles where some GPUs are just sitting there waiting idle for the output of the previous layer. Pluralis's breakthrough was solving this latency problem with massive compression. They achieved a 99% compression of the forward and backward passes.
99%. A 100x decrease in network traffic. That's incredible. How?
They discovered that the useful information, the actual signal traveling between these layers, is highly redundant, and it lives in these tiny low-dimensional subspaces. By compressing the signal and only sending the necessary subspace information to the next GPU, they drastically cut the size of the messages.
And they proved this worked.
They did. They trained an 8 billion parameter llama model successfully on low-end consumer GPUs, connected only by everyday 80 megabits per second internet links. This moves model parallelism from the lab into the living room.
And this technical setup feeds directly into their unique economic model, protocol learning, which is all about ownership.
Right, and it's based on this idea of unextractability. Because the model is layered across so many different GPUs, no single participant ever holds the full set of model weights. This creates a natural defense against theft or censorship. And crucially, contributors gain an equity-like upside. They share in the revenue generated by the successful protocol model.
So it aligns incentives. You're incentivized to contribute quality resources only to models you believe will become commercially viable and successful.
It turns the compute providers into stakeholders.
Next up, we have Templar, which is unique because it's the only one of these projects currently operating with a live integrated economic layer.
Right. Templar operates as a bit-and-sur subnet, which provides a layer for permissionless production with real-time, market-based incentives. It uses data parallelism, where miners perform the training tasks and validators score the quality of their contributions.
And how does that scoring system ensure the work is honest and productive in a totally permissionless environment?
They use what's called the gauntlet verification system, and it employs the open skill technique, which is a competitive ranking algorithm originally used for scoring players in video games.
Interesting.
Validators measure the contribution of each miner by analyzing how much that miner's update actually reduced the overall model loss. This creates a skill rating. Higher-rated miners get rewarded more with the subnet's local token, Gamma, which is convertible into the overall bit-and-sur TAO token.
So the economic incentive is directly tied to improving the AI's performance. And what's their current scale?
They started small to prove their architecture 1.2B and 8B models using their communication-efficient optimizer, Sparse Loco. But Templar recently pushed the boundaries by launching Templar III, which is a 70 billion parameter pre-training run.
70 billion.
Yes, this is currently the largest training run ever conducted in the decentralized space, and it proves they can manage immense model state and coordinate the economics necessary for frontier models.
Finally, let's look at Jensen, which based its entire design on principles of trustlessness and scale.
Jensen's framework is guided by what they call their Geo-Estli principles: generalizability, heterogeneity, overhead, scalability, trustlessness, and latency. They recognize that building a trust layer was their most crucial challenge.
And they have a specific mechanism for post-training work, the RL swarm.
The RL swarm is their decentralized coordination mechanism for reinforcement learning. It uses this three-step peer-to-peer loop that's optimized for asynchronous distributed work. First, answer, where the model generates an output. Then critique, where a shared reward function evaluates that output. And finally, resolve, where the model incorporates the best responses.
And that kind of post-training workload is better suited for decentralized settings.
It is, because the prediction phase requires less tight synchronization.
Okay, but their verification system, Vertijudge, sounds like the ultimate breakthrough for trust. If cryptographic proofs have a 10,000x overhead, How does Jensen verify work without just destroying efficiency?
This is their core intellectual property. Instead of these costly cryptographic proofs for every single calculation, they use what they call repops, or reproducible operators, to ensure deterministic mathematical outputs across different types of GPUs. So if the network suspects a node has submitted invalid work, a referee doesn't rerun the entire job.
What does it do instead?
The judge module only recomputes the single specific microstep that diverged from the expected output.
That is extremely clever. It avoids the massive overhead because the recomputation is surgical.
Exactly. This trust layer adds only a few percent of overhead, ensuring correctness without crippling efficiency. It's a very pragmatic approach to verification.
And what about Jensen's approach to communication optimization?
They focus on managing latency and ensemble learning. They have skip pipe, which addresses pipeline parallel training delays by dynamically skipping or reordering layers if a specific node is acting slow. That can cut iteration time by up to 55%. And they also use diverse expert ensembles, or HDEE, where they train many small specialist models completely independently and then merge them at the end.
So because no gradients flow between the machines during the training phase, any idle GPU can immediately contribute.
Right, it maximizes the utility of the entire global hardware pool.
Okay, we've now moved from traditional FL to the absolute cutting edge of decentralized incentivized training. But let's pull back for a moment and focus on the fundamental privacy promise. We established that FL alone does not guarantee privacy. Institutions in highly sensitive sectors, like biomedicine, they need stronger, formal guarantees.
Right, we need to combine FL scalability with formal privacy protection. And this forces us to compare the two fundamental camps of privacy techniques: cryptography versus perturbation.
The cryptographic techniques are HE and SMPC. Their focus is on pure secrecy.
Yes, they follow the paradigm. Bring data to computation. The goal is to compute on encrypted data without ever needing to reveal the plaintext. This provides privacy based on mathematical secrecy, but it assumes the cryptography holds and no parties collude.
And the opposing camp is perturbation, which is dominated by differential privacy, or DP.
And DP shifts the focus from secrecy to a statistical guarantee. It adds calibrated noise. The core idea is that the resulting model is mathematically proven to be nearly the same whether or not a specific individual's data was included. And this quantifiable privacy loss is defined by those famous epsilon and delta parameters.
So for these highly regulated sectors, the sources suggest the hybrid approach is the most viable path forward.
It is. It's the necessary compromise. You combine the computational scalability of SFL with the formal guarantees of either DP or cryptography. And this hybrid model is critical in genomics and healthcare. We're seeing frameworks combining FL plus DP for complex tasks like brain tumor segmentation, or FL plus SMPC for genome-wide association studies, or GWAS.
So this is enabling health institutes to collaborate securely while respecting those stringent patient data laws.
Exactly. Now let's leverage the comparison data from the sources to balance this triad of scalability, privacy, and accuracy. This really requires understanding the technical cost of each method. Let's start with computational efficiency. Which method performs the best and which one incurs the most heavy burden?
Okay.
FL is the best, hands down. Because it brings computation to the data and distributes the work entirely to the clients, the central server's burden is minimal. The worst performer is homomorphic encryption, HE.
And why is he so computationally punishing?
Because computing on encrypted data is just inherently slow. The HE ciphertext is much larger than the plaintext data, and operations like aggregation are extremely demanding for the server that has to perform these calculations on the encrypted data. SMPC is also poor because the few computing parties have to process secret shares from many, many clients, which leads to high overhead.
Okay, next. Communication efficiency, the network bandwidth utilization. We know FL alone is bad, but how do the others compare?
DP is actually the best here. It only sends minimal information, essentially just noise, and requires minimal network traffic. Standalone FL is the least efficient overall because it's exchanging millions of model parameters constantly.
And when you combine techniques.
FL plus SMPC is the worst hybrid approach for communication, as each participant needs to send large amounts of traffic to multiple computing parties to perform that secure aggregation.
The third metric, and the one that matters most in a field like medicine, is accuracy. How much does all this privacy protection damage the quality of the final model?
Standalone FL and SMPC are the most accurate. They incur very little loss in the final model, assuming there are no malicious actors. The methods that use approximation or perturbation, they suffer the most.
So DP is going to hurt accuracy.
Considerably. DP incurs accuracy loss due to the necessary addition of that calibrated noise. He also suffers because deep learning requires nonlinear operations, and HE can only perform addition and multiplication on encrypted data. It forces approximations that degrade accuracy. So FL plus SMPC is the best hybrid for accuracy, while FL plus DP is the worst due to that unavoidable noise.
Finally, the critical distinction, privacy guarantee. Which methods provide a formal, quantified guarantee?
This is the definitive metric. Differential privacy, DP, and its hybrid form, FL plus DP, are the only approaches that provide a quantifiable mathematical privacy guarantee defined by those specific epsilon and delta parameters.
And all the others rely on assumptions.
All of them. HE, SMPC, and standalone FL, they rely entirely on assumptions. The assumption that the cryptography is unbroken, the assumption that the central server doesn't possess the decryption key, or the assumption that the computing parties don't collude. If any of those assumptions fail, the privacy guarantee just collapses.
So if you are a major medical institution, you are facing this massive trade-off. You can prioritize accuracy and speed with FL plus SMPC, but you have to rely on assumptions. Or you can prioritize a mathematical guarantee with FL plus DP, but you potentially sacrifice your model's accuracy because of the noise.
That is the real-world decision. For biomedicine, achieving a realistic balance between scalability, privacy, and accuracy dictates the choice. And while HE and SMPC are technologically impressive, the high computational and communication costs often make them impractical at scale. Therefore, FL alone, or FL combined with DP, despite that accuracy trade-off from the noise, is generally considered the most promising route for truly large-scale, global biomedical applications.
Hashtag outro.
So we have journeyed from institutional federated learning, which was designed for regulated compliance and cross-silo collaboration, all the way to these entirely new crypto-native networks that are challenging the central power structures of the largest AI labs in the world. The technical momentum is now, I think, undeniable. Decentralized training has moved past the academic phase and into execution. We're seeing working production-scale training runs coordinating massive models across the globe, from Noose's 40 billion parameter consilience to Templar's 70 billion parameter run. The technical viability is established. You can stitch together distributed heterogeneous GPUs, and you can compress the communication efficiently enough to make it work.
But let's be real about the remaining gap here. Centralized labs maintain these staggering advantages in dedicated, homogeneous hardware, optimized software stacks, and distribution networks. They're constantly raising the bar with new technologies like NVIDIA's B200 throughput gains and the latest PyTorch and TensorFlow software optimization.
Decentralized networks have to be agile enough to continually update their custom stacks just to keep pace with the efficiency gains of the incumbents. The toughest test ahead, however, is not technical. It's economic and it's governance related. Can these decentralized projects establish the incentive, the verification, and the ownership structures, like Pluralis's equity-like protocol model, or Templar's skill-weighted scoring for TAO rewards, that can reliably attract and retain high-quality talent and resources for the long term?
That requires solving human problems of trust and alignment.
It does. And even if they build the best model, they still face the distribution and monetization challenge. If a state-of-the-art model is created on a permissionless network, how do they capture the revenue? And who will actually use that model when high-quality, free, open-source alternatives already exist?
This fundamentally defines the stakes, doesn't it? The entire move toward decentralized AI is a mandate for alignment and ownership.
It is. If these decentralized architectures can successfully translate their philosophical commitment to openness into models that offer competitive performance and, crucially, verifiable integrity proof that the work was done honestly, they will have created not just a technical alternative, but a more resilient, transparent, and participatory ecosystem for AI development.
The core technical ingredients for success, the low communication optimizers, the asynchronous schedulers, the verifiable computation, they are all on the table right now. The question for you, the listener, is this. When the technology is no longer the bottleneck, which decentralized architecture will win the long game by solving the inherent human challenges of trust, sustained contribution, and economic coordination at a global scale?